Hey guys, this is Mrs. Harbin, and today we are looking at the next section of Unit 7, which is quotients. And we've been learning all about radicals and simplifying radicals and adding and subtracting radicals and multiplying radicals. And so now, hopefully, you know that word quotient means that we are going to do some division with radicals. So let's start off with a quick review on simplifying radicals. Remember that we cannot take even roots of negative radicands. We could do odd roots, but there's no number that when multiplied an even number of times is going to still be negative. So we're going to split this into its two factors of -1 times -25. And using that product property of radicals, we know that's just the same thing as the square root of -1 times the square root of 25. And when we're talking about the square roots, we're talking about the principal roots, so not plus or minus 5. We're just using our principal roots here. And so the square root of -1 is I, and the square root of 25 is 5, and that simplifies to, that's kind of hard to see there, but that simplifies to 5i. I'll try to write the other ones a little bit smaller. All right, 8x, or x to the 8th over x cubed. Now, if we were to write that out, that would be x times x times x times x, etc., 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 8 times over x times x times x. We would then cancel, but we can also just use our shortcut, and we know that x to the 8th over x to the 3rd is just x to the 5th. We can take our 8 and subtract the 3 that will cancel, and we're left with the 5. And then we have x to the 5x plus 1 over x to the 2x plus 3. And using our same property here, we're going to keep our base the same, and we're just going to subtract our exponents. So we're going to get x to the 5x plus 1. We could write it this way. X to the 5x plus 1 minus the quantity, 2x minus 3. And when we simplify that, what we get is x to the 3x plus 4. We would have to distribute that negative there. So this becomes, let's do this work down here, 5x minus 1 minus 2x plus 3. Oops. And I just realized that's a 5x plus 1 there. Let's write that correctly, 5x plus 1. Minus the quantity 2x minus 3. After we distribute that negative, our 1 and our 3 do combine to become that positive 4. So that's just a quick review of simplifying radicals and our property of exponents, our quotient property of exponents here. So let's talk a little bit then about how we do quotients and radicals. And we're going to look at this quotient property of radicals. And what the quotient property of radicals says is that if the nth root of x and the nth root of y are real numbers, and y is not equal to 0, then the nth root of x divided by y is the same as the nth root of x divided by the nth root of y. And n is just representing any number here. So square root, cubed root, 4th root, 27th root, what have you. This is very similar to the product property of radicals here. Quotients and products here are very similar. So if we're putting numbers with that, let's say we have, for example, the 3rd root of 1/3. Another way that we can write that is the 3rd root of 1 over the 3rd root of 3. And if you think back to the product property, like the one we did in the warm-up here with that -25, we were able to split it into its factors. We said -1 times 25, and the product property then says we could write that as the square root of -1 times the square root of 25. So the quotient rule, quotient property, if you will, of radicals is very similar. If we've got a fraction in the radicand, we can just split that into two separate radicals, a numerator and a denominator. But when we do that, that creates some problems for us, and we're going to talk about those problems that it creates in just a second when we talk about whether a radical is fully simplified. So when we are simplifying radical expressions, we need to keep a couple things in mind. First, we need to make sure there are no perfect nth powers in the radicand. And what that means is this. If I have 1 over the square root of 25, this is not perfectly simplified because I've got a perfect power still down here. It can be further simplified. That can just be, 1 over 5. Or if I have 1 over the square root of 8, okay, that's also not fully simplified because I know that 8 is the square root of 4 times 2. And the product property says I can take the square root of 4 times the square root of 2. And when fully simplified, that's 1 over 2 root 2. Ooh, running out of room there. 1 over 2 root 2. So we can't have any perfect powers in the radicand. That's our first condition for it being simplified. Our second condition is that we've got no fractions in the radicand. So I cannot leave this as 1 over 5. This is not fully simplified, the square root of 1 over 5, because the fraction 1/5 is in the radicand. And the third condition for whether a radical expression is simplified is that there are no radicals in the denominator. So if you take a look up here where I simplified 1 over root 8, even though I don't have any more perfect powers in the radicand, I simplified it to 2 root 2, it's still not all the way simplified because I've got this root 2 hanging out here still in the radicand. If I take 1 over 5 and I write that as the square root of 1 over the square root of 5, and the square root of 1 is 1, and I get 1 over square root of 5, well, now I have no perfect powers in the radicand. I have no fractions in the radicand. However, I do still have a radical in the denominator. And this is an irrational number. And we don't want irrational numbers. We want them to be rational. And so the way that we fix this third step, this is kind of the process that's going to be new that we introduced today. Because we want it to be rational, we are going to do something called rationalize the denominator. And even though that sounds like something maybe really, complicated, rationalize the denominator, it's really not. It just means rewrite that fraction or rewrite that expression so there's not a radical in the denominator. And that's the process we're going to take a look at today. And I hate that this example is right here, but we're going to take a look starting with an odd root. So we'll come back to this. This is in your book, but we'll come back to this after we take a look at this example. So first of all, we want to simplify this expression. If you remember, we don't want any fractions in the radicand. We don't want any perfect roots under the radical symbols, and we don't want any radicals in the denominator. So the first thing we're going to do is what we would do in any problem. We're going to see this 2 over 12, and we're going to simplify that. 2 over 12 simplifies to 1 over 6. So we've got the cubed root of 1 over 6. We're then going to apply our quotient property of radicals and rewrite that as the third root of 1 over the third root of 6. From there, we'll see if either of these is perfect cubes, and I do know that 1 is a perfect cube. So the cubed root of 1 is 1, and the cubed root of 6 is not something that can be simplified, so it stays there. So if we're looking at this so far, we've met conditions 1 and 2. Condition 1, there are no perfect roots under the radical symbol. We're good here. We can't simplify that. Condition 2, there are no fractions in the radicand. We started with a fraction in the radicand, but we don't have one now. Step 3 is the step I said we're really going to work on today, and we can't have any radicals in the denominator. And if you look at this right now, we've got a radical in the denominator. And what we want to do is not change the value of this expression. We need to change the form of this expression. I need to get rid of this cubed root. And I know that the only way to get a cubed root is if this were a 6 cubed. If I could make this a 6 cubed, and this would be a cubed root, they would cancel each other. And then there wouldn't be a radical in the denominator anymore. So that is exactly what I'm going to do. I'm going to erase this here. And I'm going to think of a way that I can make that into a cubed root. And the way that I can make 6 to the first a cubed root is multiplying it by the cubed root of 6 to the second. If I multiplied the bottom by the cubed root of 6 to the second, I would then have the cubed root of 6 to the third, what I was trying to create. Now, because I don't want to change the value of this, I know that the only thing I can multiply a number by and not change the value is 1. Like if I multiply 5 times 1, still have 5, I didn't change the value. If I multiply 1/2 times 1, I still have 1/2, I didn't change the value. So I need to multiply this whole thing by 1. But the bottom needs to look like this. Well, thankfully, I remembered that any number over itself is equal to 1. So if I write the cubed root of 6 squared over the cubed root of 6 squared, what I'm really doing is just multiplying by 1. Anything over itself is 1. So I'm not changing the value, I'm just changing the function. If you're having a hard time remembering that and remembering what I'm talking about multiplying by 1, another helpful trick is just to remember, whatever you multiply the bottom by, multiply the top by, so you don't change the value. So let's go ahead and multiply by this 1 here, although it looks like a different 1 than we're used to seeing, and see what happens as we rationalize our denominator. So 1 times the cubed root of 6 squared over 3 root 6 times the cubed root of 6 squared gives us cubed root of 6 squared over the cubed root of 6 cubed. And like I said, I knew that I wanted these to be the same so that they would cancel. So the cubed root of a cubed number cancels. So that leaves me just 6 on the bottom because these two things cancel. And the top becomes the cubed root of 6 squared, or the cubed root of 36. If we look at our rules of simplification, I don't have any fractions in the radicand. I don't have any perfect roots in the radicand. And now I no longer have a radical in the denominator. So this, keep going the wrong direction there, has been simplified. And I said we would come back to slide 5. So let's take a look. When simplifying a cubed root, or really anything other than a square root, so anything other than a square root, you're going to rationalize the denominator by multiplying both the numerator and the denominator by a factor. That makes the radicand and the denominator a perfect cube. What that is saying, and I wanted to show this to you afterwards, is we want to multiply it by something. For example, if our index is 3, we need to multiply it by something that will also make our exponent 3. So 6 to the first times 6 squared is 6 cubed. That's what that whole little screen there was saying. All right, let's try a second one here, looking at expressions that involve imaginary numbers. Because imaginary numbers are also irrational numbers, we also need to rationalize those the same way that we would rationalize other radical expressions. So let's take a look at example here. We've got 18 over 3 square root of negative 3. The first thing I want to do is rewrite that negative 3 as an imaginary number. And when I do, I get 18. I'm going to do an intermediary step here. With that, I comes out, so we get 3i root 3. Now, this leading coefficient, 18 over 3, I can simplify that. 18 over 3 is just 6. That's where the 6 comes from. So that simplifies to 6, and I'm left with I root 3 on the bottom. Now, I don't want to leave these irrational numbers here on the bottom, so I'm going to multiply by I root 3. That would give me a 3 squared to match my index of 2. I also know that I times I is I squared, which is also not an irrational number. It does rationalize it. I'm multiplying the top and bottom by the same thing because this is just 1. Anything divided by itself is 1. I'm changing the form, not the value. And when I multiply that, I get 6i root 3 over 3i squared. I can simplify this again because I know that I squared is negative 1. So I've got 6i root 3 over negative 3. And then I've got my leading coefficients here that I can simplify one more time. 6 divided by negative 3 is negative 2i root 3. So I've got no fractions in the radicand. I've got no perfect squares or perfect whatever roots. Whatever my index is, I don't have any perfect roots. Here it's a square. And I have no irrational numbers in the denominator. All right, I've got another example for you here using imaginary numbers, but I am almost out of time on this part. So we're going to end part 1 here, and we're going to pick up part 2 with example 2b, simplifying, again, some complex numbers and looking at how to rationalize denominators when we're dealing with both radicands and when we're dealing with I.